Hi everybody, I hope you're doing well. Today's video lecture will be about computing powers of a matrix by using Jordan form. This material is based on lecture notes of May 26th, 28th and June 4th. Okay, let's start. So let's V be a vector space, finite dimensional one. Over a field F, and let T be an operator we have one condition on T. Assume that its characteristic polynomial is a product of linear factors. Is a product of linear factors in Fx. Okay, so these factors may be repeated. Let's write it in the following form. So this is the characteristic polynomial delta Tx. So suppose it is of the form x minus lambda 1 to mu 1, x minus lambda 2 to the power mu 2. This goes on until some point, x minus lambda k to the mu k. Okay. Then we know several things about T. One result that we got in the lectures was the Sherilee decomposition. Okay, what does it say? The statement is there exists a unique decomposition of T as the sum of two operators S and N, where S is semi-simple N is nilpotent and furthermore, all these three operators, T, S, and N commute. And such that T, S, N pairwise commute. Okay. Well, the proof was in the lecture notes, which I will not reproduce here. Now, furthermore, we know a little bit more about these operators. Let me write some more. So furthermore, we can write the vector space itself as a direct sum of certain subspaces, CIs, where CI is the kernel of the operator T minus lambda I times I to the power mu I. So lambda i's are the eigenvalues and mu i's are precisely the multiplicities which appear in the characteristic polynomial. Okay. Now, what is the relation to these operators? Something important that we should know is that each operator T, S, N leaves each of these subspaces CI invariant. So each of T, S, N leaves CI invariant. Furthermore, S has a very clear description. So when restricted to one of these subspaces, it is simply lambda I times the identity. So if you restrict the semisimple operator to Ci, it is exactly in this form, a multiple of the identity, and the multiplication factor is the eigenvalue. So what about n, you might ask, and that's kind of what Jordan form tells us. So Jordan form, okay, I'll not write the precise description of Jordan form, which you probably know from the lectures, but if I want to summarize in one sentence, it would be saying that, so we showed that the nilpotent operator restricted to Ci can be represented by matrices of a very, very special form. And this is the content of Jordan form. So you have this decomposition. If you restrict the semisimple operator, it's a multiple of the identity on the subspace. If you restrict the nilpotent operator, okay, you have some choices, but you can simplify it quite a bit so as to get the Jordan matrices that you have seen in the lectures. Okay. Now this was kind of the summary of what was going on. Now we want to use this. Let's talk about the powers of an operator. Okay, now the first remark is, first say T1 and T2 are two arbitrary linear operators on the vector space V. Then you might want to look at, so to say, just for example, powers of T1 plus T2. Let's compute the easiest one, except the first power. Okay, so this would be just simply T1 plus T2 times T1 plus T2. So what you should do is, of course, expand this parenthesis by using distributive log. So that would give you T1 square plus T1 T2 plus T2 T1 plus T2 square, which is not quite the same as an inequality T1 square plus 2T1 T2 plus T2 square, at least in general. Right, and reason is, underlying reason is T1 T2 usually is not equal to T2 T1. Composition of operators is not commutative in general. But if for some special reason T1 T2 is equal to T2 T1, then equality would hold. And similarly, it would give you some binomial expansion for higher powers as well. And similar for, let me just say T1 plus T2 to the power m. I mean, if the operators do not commute, then you'll have lots of terms which you cannot collect together. If the operators do commute, then you can expand this like a binomial expansion. Okay. Now, in our case, let's come back to our case. We have the Jordan-Sherilee decomposition, and the S and N in this decomposition do commute, and we want to take advantage of that. So in our case, t is equal to s plus n, and we have Sn equals ns. Therefore, if you want to make a computation like t to the power m, this is s plus n to the power m, and you can treat this like binomial expansion. So you could do s to the m plus m choose 1, s to the m minus 1, n plus so forth, all the way up to m choose m, which is 1 of course, times n to the m, right? So just like in algebra where you're doing binomial expansion. Okay, this was the first thing to note. Now let's come back to matrices, so powers of matrices. This was for a general operator. Now let's select the basis and do this power business for matrices. So suppose A is in set of n by n matrices over the field F, and to be in line with what we discussed before, suppose it has characteristic polynomial equal to a product of linear factors in fx, the same assumption. Now what do we know? We know that A has a Jordan form. So the existence of Jordan form for A tells us that there is an invertible matrix P invertible P and a J in Jordan form such that A is equal to P times J times P inverse, right? So this is what the existence result about Jordan forms tells us. Now, suppose we want to compute some power of A. We already talked about this when A was diagonalizable, but let's generalize now. A to the power m simply, sorry, this should be P J P inverse to the power m. Of course, this is like writing m of these parentheses next to each other. But matrix multiplication is associative, so these neighboring inverse matrices would cancel. The rightmost one and the leftmost one do not cancel because there is nothing to pair them with. You would be left with P times J to the power m times P inverse. Okay. Now, in principle, we know how to compute J and P. So to be able to finish the computation, all that remains is to compute J to the power m. So it remains to compute J to the power m. And let's concentrate on this for a while. Suppose J is of the following form. Well, J is in Jordan form, but it might have multiple blocks. So let's give some names to the blocks. Let them be J1, J2 up to JR. All the rest are zeros. Where JI is J1 up to JR. are the Jordan blocks of J. Okay, then computing J to the power M is really a bunch of distinct problems of computing the powers of each of these. So these blocks would not interact, and J to the M would be equal to simply J1 to the M, J2 to the M up to JR to the M. Okay, so actually the problem is reduced to computing the powers of one Jordan block. And finally, let us concentrate on that and try to finish this at least theoretically. Okay, now let's look at one of these JIs. Say JI has lambda i's on the diagonal and ones above it like this, and the rest are zeros. The first remark is that we could write this as the sum of these lambda i's, diagonal matrix, plus a second matrix where you have zeros on the diagonal but ones just right above the diagonal. Right, we have this decomposition, and this is nothing but the S plus N decomposition for Ji. So S plus N, well, it's easy to check. I mean, S is semi-simple, it's already diagonal, N is nilpotent, some power of it is 0, and they obviously commute simply because S is a multiple of the identity matrix. Therefore, this must be the S plus N decomposition for this Jordan block. Now, let us apply what we learned. If we take some powers of Ji, we can treat this like a binomial expansion because S and N will commute. So, Ji to the power M, just use the binomial formula, S to the power M plus M choose 1, S to the M minus 1N. Keep going until M choose M, N to the M. Now, okay, some remarks are in order. If, okay, I didn't say anything about the size of this matrix. If Ji is, let's say, L by L, then just by direct observation, N to the power L is 0. Please, if this is not clear, just directly compute. Each time you multiply N by itself, these ones on the above the diagonal will go further towards the corner, and on the nth power they will totally disappear. Okay, this means if M is large compared to L, then after some point on, the terms will disappear. Now, if we want to compute this, then we should understand what's S to the power M minus I times N to the power I looks like. And easy computation shows that you get exactly the following. You get zeros on the main diagonal, zeros up to some points, and this is exactly the I plus first position. So let me write an I plus 1 here. Sorry, this is the ith one. The next one is, this is the ith position. In the I plus first position, you begin to get something non-zero. So this is lambda I to the power m minus I, and this goes all the way down up to here, lambda I to the m minus I. And the lambda I to the m minus I comes from these powers of this diagonal matrix, and the positions of the ones is because of n to the power I, and the rest are again 0. Now, if you collect all of these things together by using the binomial formula, then you have a clear formula for ji to the power m. Ji to the power m. Let me write this quite in a large matrix so that we can see everything. You have lambda I to the power m on the main diagonal. Right, one step above the diagonal, you have m choose 1, lambda I to the m minus 1, and the same thing goes up to here. Then m choose 2, lambda I to the m minus 2. I guess the pattern is clear. You go on like this. If this is going to be L by L, then the last thing that you write would be, I guess, m choose L minus 1 times lambda I to the m minus L plus 1. Sorry that this didn't fit here. Okay. And you have zeros all the way down. So it's an upper triangular matrix. Okay. Anyway, we have, well, there are some slight combinatorial complications, but we have a clear formula for ji to the power m when ji is a Jordan block. Okay, now putting this all together gives us some efficient method to compute the powers of any such matrix. Okay, now for the rest of the lecture, let us work on an explicit example. Okay, the example that I'll give is also among the exercises in the last set. So, I mean, not the power, but Jordan form itself. Compute a to the power 262, where a is the following 4 by 4 matrix. 7, 1, 2, 2, 1, 4, minus 1, minus 1, minus 2, 1, 5, minus 1, 1, 1, 2, 8, as a matrix in M4 by 4 R. Okay, so the strategy is to write A equals PJP inverse, where J is in Jordan form and P is invertible. Then A to the 262 will just be P J to the 262 P inverse. We know how to compute J to the 262, so we'll be done. That's the strategy. Now, one piece of this example, which I will not do here, is to compute the characteristic polynomial. I'll just write it down. But I'll do the rest. So delta AX, it is of course determinant x times I minus A. Well, it's a straightforward computation, but a little bit lengthy. Just check that this is equal to x minus 6 to the power 4 as exercise. Okay, so lambda equals 6 is an eigenvalue of multiplicity 4. And there are no other eigenvalues. Okay, now we want to compute J and P. So let's start by looking at eigenvectors. Okay, so we need to solve A minus 6i times V equals 0, this linear system. Okay, writing it down, we have the following. Okay, now one needs to do row reduction. Okay, there are some easy observations. The first and last rows are identical, so that will cancel the last row altogether. And the second observation is maybe the sum of the first 3 rows is 0. So the sum of the first 2 rows will kind of cancel the third one. So you'll have 2 rows of zeros. And after this, it is not hard to see that row reduction gets us to this point. Okay, please check the details if you're unsure. Well, this immediately tells us that rank of A minus 6i is 2. You have 2 0 rows and 2 pivots, right? So rank nullity theorem, nullity and rank should add up to 4, so nullity is also 2. Okay, so the eigenspace is 2-dimensional. Now, this immediately puts a big restriction on the possible Jordan forms. Maybe let's concentrate on this point. Now, each Jordan block would contribute 1 to this dimension, because for each Jordan block, you would get 1 independent eigenvector for that eigenvalue. So this tells us that there are 2 Jordan blocks for this eigenvalue, but this is the only eigenvalue, so we have exactly 2 Jordan blocks. Okay, it's quite general fact and it's quite helpful. So, okay. Now we can think about a little bit of combinatorics. So what are the Jordan matrices with only 6 as eigenvalue and which have 2 Jordan blocks? So the possibilities for J. Now, a moment of thought tells you that there are 2 possibilities at this point. One is this one. You have so 6, 6, 6, 1, 1, 1, 3 by 3 block, and a 1 by 1 block here. Of course, the rest is zeros. This is one possibility. And then you have J2, where you have 2 Jordan blocks of size 2. Okay. Well, essentially you could think about these as corresponding to the partitions of 4 as 3 plus 1 and 2 plus 2. These are the only partitions of 4 which have exactly 2 pieces. So you have only these. Of course, there's 1 plus 3, but we don't care too much about the ordering of the Jordan blocks, so we just take this one. Okay, so which of these is the Jordan form of A? We have to answer this question. Well, let's look at the next non-trivial thing, the minimal polynomial. Let's look at the minimal polynomial, delta AX. Now we know that the minimal polynomial must divide a characteristic polynomial, so it must be one of the following 4 polynomials, either x minus 6 or x minus 6 square or x minus cube or x minus 6 to the 4. This is just because it must divide a characteristic polynomial. Now let us check these one by one. First of all, a minus 6i is obviously not 0, so it is not delta AX, is not x minus 6. Then you could look at the square of this matrix and see if that is 0. That's a small computation. I'll just write the results because we all know how to do it. So it gives you this matrix. It's a certain rank 1 matrix, but it is not 0. So, in particular, the minimal polynomial is not equal to x minus 6 square either. Okay, you have to go a little bit higher. But its cube, please do this, it is 0. I mean, it's a 0 matrix, which I'm writing as 0. So, we find the minimal polynomial. Okay. Fine, so we found the minimal polynomial. Now, A and J are similar, so they have the same minimal polynomial. You can just check that the minimal polynomial of J1 is x minus 6 cube. It has a 3 by 3 block, and it exactly takes the third power to kill that 3 by 3 block. But on the other hand, delta of J2, the second possibility, is x minus 6 square. Okay, so among these two, of course, the first one is the matching one. Therefore, the Jordan form, we now found it. J must be this first option, which is the one with one 3 by 3 block and one 1 by 1 block. Okay, so we found J. Now, the next step is finding P. This part is usually a bit of solving linear systems, but keeping careful track of what happens. So, the usual strategy is to write P in terms of its column vectors, v1, v2, v3 and v4. So these are the column vectors of P. It's 4 by 4, so these are 4 by 1 column vectors. Now we must have AP equals PJ, right? This is the key relation. Now if you write this in terms of columns, the left side looks like AV1, AV2, AV3, AV4. For the right side, you have to look at this particular J. I mean, so what it tells you about this multiplication, but it's easy to keep track of. Please check that. This will give you 6 V1 here, then V1 plus 6 V2 here, V2 plus 6 V3, and finally 6 V4. Please check this, that PJ is really equal to that. Okay, so we get a bunch of linear systems. We must have A minus 6I times V1 is 0, A minus 6I times V2 equals V1, A minus 6I times V3 equals V2. Right, I mean the first equation is from the first column equation here. The second equation is by comparing the second columns and so forth. And the last one is simply AV4 is 6V4. In other words, it's A minus 6I V4 equals 0. Okay, so this tells us that V1 and V4 are eigenvectors. This makes sense because we already knew that the eigenspace would be two-dimensional, and these would be kind of a basis for the eigenspace. The other two, V2, V3, are not eigenvectors. They're generalized eigenvectors. Okay, so this will be the pattern. Now, we have to find everything one by one. Well, eigenvectors we could quickly find, but the tricky part is to choose the first eigenvector V1 so that the remaining equations for V2 and V3 are also solvable. So that's what we'll do next. So for the eigenvectors, recall that our system was row reduced to the following: 1, 1, 1, 2, 2, 0, 0, 1, 1, 1, 0, and the rest are zeros. So this tells us all the eigenvectors. You have two free variables, k and l here, let's say, and the others are, you can compute from the equations, they are both minus k minus l, and kl not both 0. And one of them could be 0, but if you have both of them 0, that's trouble, because you would get 0 as an eigenvector, which you don't want. Okay. Now, this is some set of vectors, and we should select V1 from the set so that the remaining equations, A minus 6I V2 equals V1 and A minus 6I V3 equals V2 are solvable. They have a solution. And this will not happen for random choices of k and l. There will be some conditions imposed by the consistency of these equations on k and l. We'll see. Okay. Let's start from the first one. So look at A minus 6I V2 equals V1. How would we write down this linear system? Well, just write the matrix A minus 6i and on the right, for this moment, let's write the most general eigenvector, and we'll see what conditions are imposed in a minute. Okay, this is a non-homogeneous linear system, and we should row reduce it to see what happens. Well, subtract first row from the last one, add the sum of the first two rows to the third one, and so forth. So this reduces all the way down to the following matrix. I'm not writing the intermediate steps, but I suppose it's clear how to do this. What you get here is minus k minus 2l, and what you get in the last row is k plus 2l. Okay. Now, this system is consistent if and only if consistent if and only if k plus 2l is equal to 0. I mean, if it is not 0, you have some bad equation here. If it is 0, both of these are simultaneously 0. Notice that this is negative of k plus 2l, so the 0 rows don't cause a problem. So we have some room to get something. I mean, so this condition is non-trivial, but it still leaves some room to get something. Okay. In a sense, okay, this might be difficult to just pinpoint in the proof, but the proof of the existence of Jordan form says that if you are doing it right, then you will find some solutions here, at least for some choices of parameters. It will not be always inconsistent. If you are getting a completely impossible system here for whatever value of the parameters, then something must be wrong. Okay? So if k is equal to minus 2l, the solutions are of the following form. v2 equals something. You again have two free parameters in the system because it's rank 2. So let's write these as a and b. You can figure out that this must be minus a minus b. And the first one happens to be l minus a minus b. Here a and b can be any real numbers. Both of them 0, that's also okay. It still will not give the 0 vector here. Okay, so at this point, this is where we got. But we are not done because we still have one more equation which should be solvable. Let's write the condition here now. Again, write a minus 6i once again. And let us write the most general such solution here. L minus a minus b minus a minus b, a and b. Okay, so we want to understand when this system is consistent now, so we must row reduce once again. It's essentially the same row operations, but the right-hand side changes only. So, but let me write what you get in this case. You can reduce all the way down here. And what you get here turns out to be the following: L minus A minus B here, L over 3 here, L minus A minus 2B here, and minus L plus A plus 2B here. Okay. Please check my computations yourself. Okay, this system is consistent if and only if, okay, this is kind of visible, L equals A plus 2B. Okay. This equality would make both of these terms 0 simultaneously, so you would get something. So again, there is some room for a solution. Okay, now we are more or less done. All you have to do is select the parameters so that these two consistency conditions are satisfied, and then pick up the vectors. Okay, for instance, set L to be 1, K to be minus 2. We needed K equals minus 2L, so that's satisfied. A equals 1, E equals 0, and then A plus 2B is really equal to L, so that's also satisfied. So there's a valid set of parameters. So this gives you V1 equals 1, 1, minus 2, 1. V2 equals 0, minus 1, 1, 0. How do I write these? Well, V1 was up there somewhere in terms of L and K, and V2 is already here on the right side. Just put in these values of the parameters. You'll get exactly that. How about V3? You have to solve this system or write one solution of that system because it has many solutions. So just pick one solution of this system for V3. Here is 1 minus 1/3, 1/3, 0, and 0. You could check that this system that we have here is satisfied for this V3. Okay. Finally, okay, all this business about the first Jordan block, which is 3 by 3. So finally, pick V4 to be an eigenvector independent from V1. That's the only requirement, which is a very weak requirement. There are many such vectors. So I'll just pick something like minus 1, 1, and 0. This is the eigenvector that you get for K equals 1, L equals 0. You could check. It does not have to satisfy these consistency conditions up there because these were for the first Jordan block. This is completely independent. Okay, so putting these all together, gives P equals the following matrix. Now please note that we had many choices along the way. So if you do it in a slightly different way, your P and my P might not agree. That's totally acceptable. But the columns should satisfy that linear system. That's important. Okay, this is the P that we found. Just to finish the problem, let's go back A was PJP inverse, therefore A to the 262 is P J to the 262 P inverse. We now have P, we can easily find P inverse. What about J to the 262? Let's write that and finish. Okay, there are two Jordan blocks, remember? You want to take the 262 to power. Okay, we'll just write a slightly bigger one here. Now for the first 3 by 3 block, that's the non-trivial part. Diagonal entries are 6 to the power 262. This is the 3 by 3 block. Then below here you have zeros. It's going to be upper triangular. Here on these two entries are going to be 262, choose 1 times 6 to the 261, 1 power less. And the corner element will be 262, choose 2, this is a 2, times 6 to the power 260. These are zeros, these are zeros. And this 1 by 1 block, that's easy. You just take 6 to the 262 and we are done. So J to the 262 is this complicated matrix here. You have P inverse, so essentially you found everything that you need. Okay, so that's all for today's lecture. Thank you very much.